So, hello, dear colleagues. I'm glad to start our next research talks within the Ukrainian Scientific and Educational IT Society. And today we are glad to host Professor Chanwoo Kim from Korea University. And he will talk about advances in on-device speech recognition and natural language processing. Professor Kim, the floor is yours.
Yeah. Thank you very much for introducing me, and it's my great honor to have a chance to talk about what we did as Samsung and our current research at Korea University. I'm currently a professor in the Department of Artificial Intelligence at Korea University, and I joined academia in this year, and till last year, I was working for Samsung Electronics, and I was in charge of language and voice technology. And I have been primarily working for speech recognition, speech synthesis, and I joined Samsung in 2018. So before that time, in the United States, I used to work for Microsoft speech team and the Google speech team. And I started working for Samsung Electronics in Korea in 2018. And at that time, I thought that Samsung is like a device company. Compared to Google or Microsoft, I thought that Samsung's advantage might be Samsung manufactures a lot of hardware. In fact, Samsung manufactures roughly 500 billion devices a year. So because Samsung is a device company, probably it might be a good idea to compete with other companies, especially focusing on-device processing. So I started working for on-device speech recognition and on-device text-to-speech. So I actually included a link to the video, but because lack of time, I probably skip on this video. But we started on commercializing our own device speech recognition from 2019. So in this page, you can see some advances in.
Yeah, Professor Kim, we can't see your screen.
So you mean you cannot see my screen?
I mean that you are not sharing.
Sorry. That's it. Sorry, I didn't know that. Sorry.
Yeah, we can see it now, but not. Yeah, okay.
So in the screen, you can see the link to the video. So if you are interested in this video, then you can probably watch the video and content. So so we started on commercializing on-device speech recognition system roughly from 2018, and on-device speech recognition was featured in Galaxy Fold, probably Fold 2 launch event. So this is a part of the Galaxy on-board event video. So in this slide, we can see some important papers and important algorithms which happened in the past 10 years. So so I use three different colors, the blue color and the also green color. So blue color means that those are algorithms for natural language processing, and the yellow colors means that those are for speech processing, and the green colors mean multimodal processing. Before 2010, we have been using traditional algorithms like rule-based algorithms or hidden model or Gaussian mixture model based algorithms for speech recognition. And also for natural language processing, we have been using grammar structures, syntactic structure, and so on. But roughly from 2012 or 2013, techniques based on neural network became very popular, and it started showing better performance than traditional approaches. In speech recognition, one important algorithm appeared in 2014, and it's called listen attendance pair. First, encoder-decoder approach appeared in the natural language processing, and that approach was also adopted in speech recognition as well. So it happened in 2014 and 2015. At the time, I was working for Google Speech Team, and I saw that some intern students started working for this kind of project. And as you probably know, WaveNet paper was published by Google DeepMind in 2000. I think it probably 2016 or so. In WaveNet, instead of using conventional technology, we can use neural network-based approaches to generate audio waveform from speech features, and also Tapotron approach appeared. And roughly from 2017 and 2018, self-supervised approaches have become popular. First, BERT paper was published, I think, roughly in 2018, and the Google T5 is based on the encoder-decoder structure. And as you probably know, generative pre-trained transformer also appeared in 2018, and the GPT-3 became very popular in 2020, and these days GPT-based approach even improved. So you can see some examples such as GPT-4 or Beta Llama. So those are quite good large language models. So in the past 10 years, there have been a lot of innovations in speech and the language processing. And in my case, I joined the Samsung 2018. So I finished my PhD in 2010. And between 2011 and 2012, I worked for Microsoft Speech Team, and I joined the Google Speech Team in 2013. So I worked for Google Speech Recognition and the Google Home till January 2018, and after that time, I returned back to my home country and started working for Samsung Research. And so I was in charge of speech recognition, and later on, I was also managing natural language processing as well. So we commercialized our internal independent speech recognition engine, both for on-device application and the cloud applications, and also we commercialized motion translation and the large language models and so on. So those are what we did at Samsung with my team members. So before talking about speech recognition and the natural language understanding in detail, I first briefly talk about some basic theories. So I think that probably you might be very familiar with the concept of machine learning. In machine learning, our objective is we are trying to build a model which can mimic the relationship between the input and output, which can be found in the training database. So suppose that there are capital I examples in the training database, and each example can be represented as a pair consisting of X and Y. X is the input and the Y is the output. So you can see some examples of those data points. In natural language understanding, usually the objective is identifying the user intention. So in this case, the ground truth is represented by the red color. So in means intention. So when the user says look that album, then user's intention is boom music. So those kind of intentions are predefined. And also there are slot values. So slot values are some specific values which might be associated with that intention. So in this case, when the user said repeat the last album, then a user's intention is be playing the music, and the slot value is the music type, and the music type itself is the album. So in natural language understanding, our objective is finding out the user's intention and slot value. In the trained database, we have data consisting of the input text and the ground truth intention and the slot value. Sorry. Similarly, in speech recognition, our objective is finding the relationship between the audio waveform and the text. In speech recognition, we store the audio waveform and we label those waveforms in text. So in speech recognition, our objective is finding out the text corresponding some spoken utterance. In a similar way, in computer vision, then the input itself can be the image, and the output Y is the class. So in this case, there are three different kinds of animals. So in supervised training, usually we have the input and the ground truth, and those are represented by X and Y. So in machine learning, our objective is predicting the Y value given the X value. So in training the model, then our objective is reducing the loss function. So in this case, the losses are represented as L. So usually we use the cross entropy loss. So and we use the conditional probability density function. So here the X is the input and the C is the class index. So when J value matches the ground truth, then the probability will be 1. Otherwise, the value will be 0. So in case of the ground truth, which is Y in this page, then it can be represented as a kind of one hop vector. So for the correct class index, the conditional probability density function will be 1, and for other classes, the value will be 0. So it can be represented as a one hop vector. And in case of the model, then in the typical case, then there will be capital C classes. So capital C here means the number of classes, and for each node, it corresponds to those estimated conditional probability density functions. So as a whole, it can be represented as a vector, and so on. This one is the predicted output vector. So predicted output vector itself is the set of the predicted conditional probability. Our objective is making this y hat vector very close to the ground truth one half vector. Then the question might be, what might be the criterion to measure the difference between the ground truth and the estimated value? And as you probably know, there is a equation like this one. So here on HPQ is the cross entropy, and the cross entropy itself can be represented as the sum of H over P. So H over P is the entropy of some probability, and the D sub KL means the KL divergence. So KL divergence actually measures the distance between two random variables. And in case of cross entropy, then H over P is actually the fixed value. So P is a random variable for the training database, and the Q is the estimated probability density function. And in case of H over P, it's a fixed value. So if we minimize this cross entropy, then it means that we will minimize the KL divergence. So it means that we will minimize the distance between the conditional probability and density function from the training database. The distance between the conditional probability density function from the training database and the estimated model prediction. So then by minimizing cross entropy, you can clearly see that the model prediction will become closer to the training database distribution. So now then we can probably understand the concept of the cross entropy training. And but for speech and language processing, usually we need to handle sequences. So in image classification, we have one single input image, and we need to classify the target class. So image classification is like this one. So there will be one image, and we need to find out the corresponding label. But in case of a speech or text, usually the input and the output can be sequences. So in that case, we don't have a prior knowledge about what might be the lengths, and for different examples of the sequence lengths might be all different. So we need to use a technique to handle of those kinds of sequences. So for to handle the sequence, the approach itself is still very simple. So we assume the conditional independence assumption, and we are just adding up the process entropy at different time steps. So if we compare the equation here in the upper side of the slide and the lower side of the slide, then the equation itself is the same, but the only difference is that in the lower side, then you can see the summation with respect to time t. So you can just represent it as a summation, because we assume that at different time steps, the probability of density function will be independent. So this assumption is not, of course, correct, but without assuming this, then it's not possible to easily interpret those functions. And it also in the upper hand side and the lower side, there are three equations, but all of them are actually equivalent. So in the top right, I use the vector notation, and in the middle line, I use the conditional probability, and usually the conditional probability will have the value of 1 for the true variable index, so it can be represented in this way. So all those three equations have the same meaning. So so now I'll start talking about RNN, recurrent neural network. So LSTM is one example of the RNN. So RNN stands for recurrent neural network, and in LSTM, LSTM is a kind of one example of the RNN. And in LSTM, there are two states. One is C and the other is H. And the C is the state that we are trying to control, and it's called the cell. And in RNN, those two states are stored, and when we have a new input, then this input itself is concatenated with the previous hidden output value. And we have three sigmoid functions, and you probably know that the output of the sigmoid will have the value between 0 and 1. And if you see the diagram, then the output of the sigmoid itself will be multiplied with some other variable, because the value between 0 and 1 will be multiplied with another value. The effect itself is this value will become either 0 or 1. So those sigmoid functions will work as a kind of switch. So if the output value becomes 0, then it means that the value of CT minus 1 will not be propagated to the current time step. And if the value becomes 1, then all the information in the past will be propagated to the present time step. So those are considered as kind of switches. So it's called a gate. So it can either be closed or it can be open. So by using the Fourier gate, then it has the capability to control whether the state CT minus 1 will be propagated to the current time step, or whether it will be completely forgotten. And for new inputs, then we also need to determine whether the new input needs to be also added to the cell state. So this one controls the input part. And in the cell, and there are a lot of information stored, but we need to control the output. So in as an analogy, if we represent it as a kind of human brain cell, then there are a lot of information in our brain, but we should not talk to everything that we know. So we need to control one need to say depending on the current input and our current state. So the output gate will control what kind of information will be sent out. So there was three such gates. So if we understand this kind of rule of each gate, then we can just draw the diagram easily, and we can write down the equation. So using this RNN structure, then we have the capability of converting variable length sequence into a fixed length vector. So as you can see, if we unknown the RNA structure, then the input can be a variable length. But if we only focus on the final hidden output, then the length itself is fixed. So the RNN has the capability of converting a variable length sequence into a fixed length output. And in the same way, we can construct a decoder. The big difference between the encoder and decoder is that in decoder we have the feedback structure. So this is called the regressive structure. And in decoder, it has the capability of converting a fixed length vector into a variable length sequence. So if we connect the encoder structure with another structure, then the whole structure has the capability of mapping variable length into sequence into another variable length into sequence. So this is the first approach to perform sequence-to-sequence mapping, and the paper appeared in 2014. This kind of approaches were first deployed for motion translation. And two researchers published the paper almost at the same time independently. And in case of Ilias Susquever, he used the same parameter both for encoding and the decoding, and he used the decoder-only structure. And as you probably know, these days GPT is based on that kind of structure, and you can probably notice that he was one of the co-founder of the OpenAI. So I talked about the encoder-decoder structure, and also Ilias Susquever proposed the decoder-only structure, which can do both encoding and decoding, and those kind of structures are now popular for large language models. But back in 2014, he didn't use pre-training. So the biggest difference between the GPT these days and the original sequence approach is that these days we are doing pre-training for generating language model. Then usually our objective is predicting the next token in the pre-training stage. And after pre-training is done, then we are doing fine-tuning with the very defined instruction following set. But in the original encoder-decoder approaches, even though that kind of RNN has the capability to store information of variable length utterance, it has been observed that if the input length becomes too long, then some information in the past will be forgotten. So the motion translation performance will go down as the sentence length increases. So this figure was adopted from Badanow's paper in 2015, and why blue score is a kind of evaluates the quality of translation performance. So then we observed that because we use the fixed size vector to connect the encoder and the decoder, then maybe the bottleneck. So in attention-based approach, instead of just relying on the final hidden output, we are calculating the correlation between the encoder and the decoder, and we use the entire history. So in the original encoder-decoder approach, we only use the final hidden output, but in attention-based approach, that we are calculating the correlation entire hidden output from the encoder side. So it's quite natural that encoder decoder approach for worse than the attention-based approach, because the attention-based approach will use the entire history. So attention-based approach appeared, and in the paper titled "Attention is All You Need," they use this kind of equations, and they use the Fourier vector, T vector, and value vector. So in encoder decoder attention, Q is from the decoder side, and the T and the values are from the encoder side. And for self-attention case, then Q, K, V are all the same vectors. So in case of the self-attention in the encoder side, then all of them are the encoder vector sequences, and in case of the decoder self-attention, everything is from the decoder side. So the biggest difference between the encoder-decoder approach and the attention-based approach is that in attention-based approach, we store all the history within the context in the memory, and we calculate the correlation, and the reading is based on that correlation, and that attention rate will be eventually multiplied with the value. So this will reduce the output of the attention. So those QKV are actually sequences. They can be represented as a matrix, but those are actually sequence of row vectors. So QKV are row vectors, and when we are calculating inner product, usually regional representation, right? X transpose Y, but because those are row vectors, the equation is Q times K transpose. So inner product is just calculating a kind of correlation, and to normalize a value is divided by a square root of it. So in scale without product of attention, because those are sequences, then you are basically calculating all possible correlation between Q and K. So it's quite obvious that attention approach will perform better than the encoder-decoder approach, because in original encoder-decoder approach, we are only relying on the final output, and in LSTM-based RNN approach, then you are using a fixed sizes cell memory, but in attention-based approach, then we are storing all the past information in memory, and we are calculating the correlation of all possible combinations. So the performance of self-attention is better than RNN-based approach, and also it shows a better performance than a vanilla encoder-decoder approach. But the downside is that the computational cost will increase quadratically as the sequence length increases. So computational cost itself might be the problem. And after that, we are applying this submax. So in the original equation, we see the submax equation here. So submax will calculate the rule direction. And in multi-head attention, we are using projection. So we can focus on different parts of the input. So we are usually using 8 heads or 16 heads, or and in case of large language models, that we can like 32 or 64 heads, and so on. Then we will have the power to making some attention to different parts by using multi-head attention. And if we only use the vanilla attention, then we are only relying on a kind of correlation information and we that use activation. But in neural network, we should use some kinds of activation. So in transformer structure, on top of the arcade potential structure, they use the value activation, and there are two linear layers. One is below and one is on top of the value layer. Usually, in the lower side, it increases the dimension by a factor of 4, and in the upper side, the dimension will be reduced back to the usual dimension. And to train in neural network, they use the skip connection, and there are layer immunization here. So this structure is the transformer block structure. Now I'll talk about speech recognition. In speech recognition, you can use the either encoder only structure and transducer structure, and also attention-based encoder structure. When I first joined Samsung, at that time I first focused on the attention-based encoder-decoder structure because that approach was very popular for motion translation. So we first commercialized attention-based encoder-decoder structure in 2019. And that product itself was a very challenging product, and we commercialized it on the world first on-device independent speech recognition system on Samsung mobile phones. And one downside of the attention-based encoder structure is that for speech recognition, we should have a streaming capability. So while I am speaking, the text will be transcribed immediately. But in the original encoder-decoder structure, the decoder will start working only when the entire input utterance is encoded. So because that kind of limitation, the latency will be very large, and it's not desirable for commercialization. So we use the streaming attention approach. And this days for speech recognition, transducer-based approach is more popular than attention-based encoder-decoder approach. So in the transducer approach, then you can see two different blocks. So you can see the decoder block in the green color, and also there are some layers in the yellow color, and we are usually using the Bidirectional structure in this part. So this is called the prediction network. So the role of this part is similar to a language model. So this block will predict the next token, and this part will interpret the speech, predict the text from the speech. So this part is more related to the acoustic part, and this portion is more related to the language part. So those two parts are combined in the joint network. So in the joint network, by using the information from the language side and the acoustic side, find that recognize speech will appear here. And in the language model side, then similar to a decoder only language model structure, you can observe the feedback structure in this way. So we first commercialized our speech recognition engine on Samsung phone using this kind of structure, and from 2020 or 2021 to this structure. And at first we used the LSTM based approach in 2019, but from 2021, we started using the conformal structure. I will explain what conformal means later. In conformal, the structure itself is very similar to the transformer structure that I explained just ago. So in transformer structure, I mentioned that in the lower part we have the multi-head self-attention, and in the upper part we have two dense layers, and we have the value activation between those two dense layers. Dense layer and linear layer being the same thing. In conformal structure, there's one additional block, so we have the convolution module. So the motivation of the conformal structure is to use the global context. We use the multi-head self-attention, but to exploit the local context, then CNN might be doing better than self-attention to capture some local information. So in conformal, we are using both the CNN structure and also attention-based structure. So those two structures are used simultaneously to use both the local and the global context. So in this page, you can see the block diagram of the convolution module and the self-attention module and the feedforward module. So the idea itself is similar to the original transformer paper, but there are some changes. So and this paper appeared in 2020 by Google people, Google speech people. So I used to work for that Google speech team here at the 18. So my former colleagues published papers about the conformal structure, and at Samsung we also use the same structure. And for speech recognition, we can also use the encoder omni structure. And if we use the encoder omni structure, then one advantage is that if you compare the encoder structure, then there's no feedback path. Then it means that to obtain the output at the next time step, if we have the feedback path, then until we calculate the output at the previous time step, it's not possible to calculate the next output, because the computation should be done sequentially because of the feedback path. And if we use those kind of non-auto-regressive structure, then the advantage is that when we are calculating the output, then the output, the calculation will not depend on the output at the previous time step, so we can parallelize the computation, so we can more efficiently use the computational resources. So if we use the encoder-based approach, then the problem is that the length of the model output will be basically the same as the input sequence length. But for speech recognition, there is no guarantee that the output length will be the same as the input length. So as an example, when the text is integer raises, then in the waveform, there's no alignment information, and also the length of this sentence itself is not the same as the length of this waveform. So we should have some mechanism to align this text with this waveform. So in CTC-based approach, we consider all possible alignments between the model output sequence and the longitudinal text. So CTC losses are calculated by adding up all those possible alignments. And Previously, I mentioned that these days self-supervised training is popular, and in speech recognition, one important paper was published a few years ago, and the paper title is Creative Today 2.0, and this paper was published by researchers at Meta, and they used the encoder-based structure, and they use some kind of masking, and masking means that some input sequences will be deleted, and the model will predict the deleted part. So without using the text label, pre-training is done using a structure somewhat similar to masked language model, and after that, this model is fine-tuned to some real labeled data. So this is an application of the pre-training strategy for speech recognition. And unlike text in speech, the data itself is a kind of continuous value. So to the best language model, then we need to have a kind of discrete unit. So to do that, vector continuation is employed. And as mentioned before, masking is done, and the contrastive loss is used to predict the masked part, and just using a very small amount of labeled data after fine-tuning, they show that the performance is quite good. So at Samsung, for minor languages where we cannot have a lot of labeled data, examples might be like some Arabic language or some um, um, Hindi dialects. We don't have a lot of labeled data. In that case, we first collect a lot of unlabeled data first. Usually, collecting unlabeled data is easier than making labels. So after collecting a lot of unlabeled data, then you can train the model with this kind of structure, and just using a relatively small amount of labeled data, then we can do fine tuning using the CTC loss, which we explained just above. So for low resource language, this kind of self-supervised training approach was quite effective. So this page I explained those functions used in BERT-based 2.0, but I'll skip this slide. And if we use the vanilla encoder decoder approach that, as I mentioned before, we cannot do streaming speech recognition. But for on-device speech recognition, so we need to reduce the latency, and to reduce the latency, then streaming speech recognition should be enabled. But if we use the vanilla encoder decoder approach, then as I mentioned before, the decoder will not start working after until the whole encoding procedure is done. So it means that while the user keeps speaking, the output will not be generated at level which is not desirable for commercialized speech recognition system. So we adopted the idea in monotonic or chunk-wise approaches. So when we first commercialized our speech recognition system in 2019, we used the 2 layers of attention, and in the lower layer, the attention mechanism finds out which part of corresponds to the text, and in the upper attention layer, then we are using our like the attention approach. So we use the 2 layers of the attention layers to enable streaming speech recognition. So This is the diagram in monotonic chunk-wise attention approach. So in the original full attention approach, so here x-axis is the time direction, and the y-axis in the downside is the outer wave index direction. So in the original full attention approach, then the attending point can be everywhere. So to do that, actually the entire encoder output should be ready. But in speech, then usually we know that the relationship between the speech waveform and text will be monotonic. So based on this, then we are finding out what might be the encoder portion corresponding to the next text. So those are calculated using the attention rate, and this is called the hard monotonic attention approach. And after finding out those hard monotonic attending points, then we construct some short ranks context window, and then within that chunk, then we calculate soft attention. So in monotonic chunk-wise attention, we use those two attention layers simultaneously. So because I already explained the transducer structure, I'll skip this slide. And for on-device speech recognition, there are limited hardware resource, so it's very important to reduce the model size. To reduce model size, we use the various kind of techniques like knowledge distillation and computation. When we commercialized our speech recognition for Samsung mobile phones, we use CPUs, and on CPU, usually there are not any 4-bit or 2-bit ALU. So, but it's equipped with 8-bit ALU. So we converted the weights into 8-bit integer values. So we perform the 8-bit computation. But for large language models, we did a further optimization, and we use the NPU. And in case of the NPU, if we can do computation down to 4-bit, then we can further reduce the model size, and the NPU also can efficiently calculate 4-bit data. So for LLMs, for on-device LLM applications, we use the 4-bit computation. And we also use the low rank of approximation to reduce the matrix size. So in depth of attention or linear layers, everything is basically matrix multiplication. And by using the singular value decomposition, then you can represent the matrix in 3 different parts. And for by using the low rank approximation, we can reduce the matrix size without causing too much distortion. And also we can do the pruning approach. In pruning approach, we can either remove some weight, which might be close to 0, and the other approach might be, especially large language models, we can prune the entire layer, or we can remove some paths in the multi-head attention approach. So those are called structural pruning, and weight pruning is kind of unstructured pruning. So those approaches are used for commercializing our speech recognition systems. We use the AP quantization, and in the initial version, we use the full rank approximation, but in the later version, we use the knowledge distillation more often. And for large language models, we use the quantization and also LoRa fine-tuning approach, which is related to blue network transformation. And we also explored layer pruning, but when you perform the layer pruning, performance degradation was inevitable. So the commercialized system, we didn't use pruning that much. Because there over time, I will skip this part and I will quickly talk about the natural understanding part. So in natural understanding, as mentioned before, our intention is finding out the user intention and the slab value. And these days, we are using BERT-like structure. BERT is the acronym of bidirectional encoder representation from transformers. So we are using the encoder portion of the transformer, and we are doing fit training. And the fit training is very similar to what I explained related to Weighted 2.0. Actually, Weighted 2.0 was inspired by BERT approach. In BERT, without using labeled data, they use mask range model. So it's often abbreviated as MLM. So we apply some kind of random masking, and the model tries to predict what might be the mask part. So instead of being trained for a specific task, when in the pre-trained stage, the BERT model will learn the language structure itself. So in the pre-trained structure, it understands the language structure itself, and after pre-training itself is done, then we are doing fine-tuning with a relatively small amount of labeled data. So here, NLI means like natural language inference and named entity recognition and the question and answering for those tasks. The pre-trained model will be fine-tuned, and usually the performance is much better compared to models without pre-training. So this kind of example shows that instead of just using the data for specific domain, usually it's better to use a lot of unlabeled data, and if the model can understand the language itself, then performance will be generally better than fine-tuning. So I will skip on this part. So in joint BERT structure, using a single BERT structure, we predict the user intention and the slab value. For example, the first token is usually called the CLS tokens. CLS means classification. So CLS itself means classification, and the intention value is predicted corresponding to the CLS position location. And in case of the slab values from the input occurrence of the model will predict where the specific slab portion starts and ends. For example, the input occurrence is play blah 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 some red rest blah blah. So this is kind of song name. So in this case, the model predicts that the user intention is play music, and the model can predict the song name. So when we are using this kind of BERT model, so at first we are using the pre-training strategy, as I mentioned before. And after doing that, using the labeled data, you can fine tune it. So by using this kind of approaches, then we can build a system which can understand the user intention. So we use this kind of approaches for our own device Bixby, which is use assistance for Samsung mobile phones. So I explained the approach, and this days large language model is very popular. And in the large language model, we are using the decoder part of the transformer structure. So in that case, we have the feedback loop. So in this diagram, output itself feedback into the input. So the structure is the output structure. In the decoder only model, then the attention itself will be the folder of attention. In encoder-based approach, usually the attention itself is bidirectional, but in decoder only structure, the attention is separated in folder direction. So in the decoder only structure, usually the training procedure is at first we are doing pre-training, and the idea is somewhat similar to masked language model, but in that case we are predicting the next output. So we are predicting the future output. So pre-training is done in this way. So we are collecting a lot of data from the internet website, and we are doing pre-training using unlabeled data. And after that, we are doing fine tuning, and we can also additionally use it in enforcement learning. So this step is called RLHF. So RLHF means enforcement learning from human feedback. So we can also use the feedback from another AI system. So that's called RLAIF. So we can use the feedback either from a human or other AI system. So we can build a reward model, and using the reward model, then we can perform the enforcement one to further improve the performance of the model. So basically, this is the structure for training the large language model. And compared to the previous dedicated model like speech recognition or natural language understanding model, the advantage of those kind of generative model is that by showing some examples, one model can be applied to different tasks like summarization, Russian translation, natural language understanding, and so on. So before the appearance of a large language model for specific tasks, we needed to build the specific models for each task. But if we use the generative language model, then one model can be applied to many different types of tasks. And I'll probably skip this part. So in today's talk, I talked about some basic theory of the sequence modeling, and I explained the encoder-decoder structure, which is initially based on the neural network, and I talked about the limitation of the encoder-decoder structure, and I explained how attention-based approach overcame on that limitation. And based on the encoder-decoder attention-based approach, self-attention approach appeared in 2017, and that's the transformer structure. And in speech recognition, we can use either encoder-only structure or attention-based encoder-decoder structure or transducer approach. And I mentioned that at Samsung, we initially used the attention-based encoder-decoder approaches in our initial commercialized models in 2019 or 2020. And to commercialize encoder-based attention-based encoder-decoder approach, then we should use streaming of attention. So I mentioned that we use the 2 layers of attention, and these days we are using the transducer approach more often than attention-based encoder-decoder approach for speech recognition. And for natural language understanding, I briefly talked about BERT approach. In BERT approach, we are using the fit training by the mass range model structure, and in joint BERT structure by fine-tuning the BERT structure to predict both the intention and the slot value. It can be used for natural language understanding, and these days generating model is especially popular, and the advantage of the generating model is that a single model can be deployed for various kinds of tasks like summarization, question translation, natural language understanding, and so on. And these days, those kind of generating language model is now evolved into multimodal model. So in the last year, GPT appeared. So in GPT, the large language model itself was fine-tuned to speech task as well. So one language model can handle both text and speech. So one model can do natural language processing, speech recognition, speech synthesis, and speech translation, and so on. So this is the end of my talk today. So if you have any questions, then please let me know. Thank you very much.
Thank you, dear Professor Kim. Colleagues, do you have any questions? I believe that we have one in the chat. So are there any alternative RNNs beside LSTM? For example, neocognitron?
Could you please repeat your question, please?
Yeah, are there any alternative RNNs beside LSTM? For example, neocognitron?
Yeah, so at Samsung, we usually use GRSM structure, but GRU structure is also very popular. So in case of GRU, then we needed to use one less gate, so the model is more compact. But when we did the experiments to accomplish the same level of performance, actually the more number of cells would be required. So entire other parameter except was quite similar. And these days, there is a structure called I forgot the name. Mamba structure. Mamba paper appeared in this year, and that has the that approach shows better performance than transformer when there was some computational research limitation, and also it overcame the limitation of the RNN. So Mamba itself is not the traditional RNN structure, but I think that it's kind of improve the structure of the previous RNN-based structure. So this says Mamba-based structure is popular, and just in this month, I think that Welcome LLM structure based on Mamba structure also appeared. So user or other alternatives.
Okay, thank you. And another question, what are the prospects for the development of the architectures like XLSTM, BiLSTM, and so on?
Yeah, so the question is apply terrestrial.
Yeah, what are the prospects for the development of architectures like XLSTM, BiLSTM, and so on? You can see actually that question in the chat.
Yeah, so in our case, when we commercialized our speech recognition system for Samsung phones, we use the unidirectional LSTM. So usually, bidirectional LSTM shows better performance than the unidirectional closure LSTM because it uses the feature values as well. But to reduce the latency, especially for on-device applications, we needed to use the unidirectional LSTM structures. So we usually use the unidirectional LSTM structures, but because a bidirectional LSTM is doing better than the unidirectional approach, when user finishes speaking, then at the top layer, we just added one bidirectional LSTM structure. So when the user finishes speaking, then another decoder step starts, and just using one bidirectional LSTM structure and full attention, the output is recalculated once again. So that approach is not performing as well as a full bidirectional LSTM structure. But if we use the full bidirectional LSTM structure, then the latency issue is quite severe. So by using that kind of hybrid approach, we could maintain the performance level while reducing the latency. And these days, instead of using LSTM, we are frequently using the conformal or transformer structure. And when we use the conformal or transformer structure, actually the story is also the same. So instead of using the full attention, we are using the limited context attention, and we are using the causal attention, especially when we are for the model for on-device application.
Okay, thank you. I believe that was everything. Thanks a lot for Professor Kim for your time, and thank you for everybody who joined us or who watched that webinar in recording. Please join our social media and join our next events. Thanks again, Professor Kim, and stay safe, everybody.
Thank you very much. Thank you.
Thank you. Bye-bye.